Hello everyone, welcome to our Google Hangout today. Today we will be co-hosting the Hangout with Swissbit. Today we have Grady Lambert here. He is the Director of Embedded Engineering from the Swissbit. Today's topic will be Swissbit solid-state drive selection criteria. If you have any questions for Grady during the course of the Hangout, please go ahead and send them to Twitter, hashtag DKHOA. And with that, I'd like to introduce Grady, and thanks for joining us here in Deep River Falls. And we'll go ahead and kick it over to you for your presentation.
Great, thank you, Nick. And thank you everyone for joining this morning's presentation. Today we're going to cover various topics in terms of SSD selection criteria for embedded applications. At the end of this, we'll open it up for questions. So we'll start with going through the different market segments for how SSDs are used in each segment, and then we'll talk about the criteria for what are selected in these SSD markets and used. Also, we'll talk about the criteria that are most important for embedded applications and why. Lastly, we'll consider what factors should be considered when you're selecting an SSD solutions provider for your application, and why Swissbit, and what are the key takeaways. So the background here is that SSDs are taking over. Embedded systems are highly pervasive. In 2011, 1.8 billion embedded systems shipped per IDC. In 2015, that number will change to 4 billion. So, sorry. Okay. Embedded systems are fixed function systems. They typically, in different applications, from automotive to telecom to medical equipment to gaming, digital signage, industrial controls, they touch many different areas. The commonality here is that it all require non-volatile flash storage, code, and data. The ecosystem for embedded systems includes various platforms. Some numbers are up to 16 different real-time operating systems. A lot of these are in-house or homegrown operating systems, different processors, different chipsets, and file systems. The applications include booting, data logging, performance cache, and system recovery. And the environments vary in temperature and voltage, shock and vibration, and specific storage requirements include reliability over life. Excuse me just one second. What's happening here? Okay. Let's try that. Sorry. So the specific storage requirements include reliability over a long life. There's a power fail safety requirements. You can't lose data when you lose power. And also, customers want to know what the health monitoring capability and tool sets are, how you monitor the life of the drive over the usage. Also included are to make sure our advanced flash error handling techniques. The key challenge here is bringing products for these types of applications, and most of the conditions are not always known. The SSDs market. The SSD technology is a market-driven technology. In 1992, SSDs were just coming out. They were mostly linear flash-based cards, PCMCIA cards, and they comprised a very small percentage of the market, but all of that market was devoted to embedded applications. In 2010, the market changed drastically over that period of time. If you'll recall, back in 2000, people were using compact flash cards for their cameras. So all that enablement created a much more bigger market for client. From 2010 to 2014, we saw a lot of increase in the enterprise sector as well. Meanwhile, the embedded part of this, it really controls a very small part. So it doesn't drive a lot of the technology, but it rather leverages the technology from the client and enterprise side to use an embedded. So we have to figure out ways to balance between those two. So when we look at these market segments in more detail, client or consumer is typically driven, used in laptops, ultrabooks, tablets, and smartphones. The application here is OS storage and user data. The usage model is mostly read, and it's a very light duty cycle. We use our laptops less than 8 hours a day, and the temperature is very comfortable 10 to 50 C. The typical service life for this drive, for this application, is 1 to 3 years before we go out and buy a new iPad 6. The bottom line here is it's all about price and performance in the client space. We want a low price, and we want to have instant on when we push the button. We want instant back. On the other end is the enterprise or data center. Here, servers, storage arrays, and those types of things. And the applications are big data, and it's a lot of transactional processing. The key here, the usage model is high performance, read-write. It's a 24/7 duty cycle. The temperature is similar to client. It's a very well managed 20 to 50 C. And the service life is on the order of about 5 years. Here, the key bottom line is that the performance, the capacity, and endurance are the primary factors, and redundancy. Cost here in the enterprise space is really measured in transactions per second. For the embedded space, it's a little different. Again, all of these embedded systems are typically fixed function compute systems. They do one thing, and they do it very well. And the application is OS, code storage, and user data. It's a wide range of mixed workloads depending on which piece of the embedded segment that you get into. For example, gaming applications are largely read-only applications, but other applications such as data loggers or industrial controls have a much more mixed workload. In all cases, for embedded systems, it's typically a 24-hour duty cycle, and the temperature range can vary from 0 to 70 or even -40 to +85. And one key difference is that at most embedded applications, the service life is anywhere from 8 to 10 years. And lastly, the bottom line here is about reliability, endurance, and life cycle management. These systems are typically considered mission critical. If the system fails because of the SSD, then that fixed function compute system doesn't work, and there's a quality of service problem in the field for the customers. It's lying down. When we look at the design points for SSDs by market segment, even more detail, we can see how they vary. Here are just a few of the different design points that should be considered in SSDs. For the interface, the primary interfaces for SSDs are ATA, USB, SD, eMMC, SATA, SAS, and PCIe. When we spread that across the 3 different market segments, you can see that they get very compartmentalized. The client consumer is mostly USB, SD, eMMC, and SATA, whereas on the enterprise side, it's SATA, SAS, and PCIe, and the latter two being the more predominant these days. In embedded space, it's a mix of the two. And as we go down through these different attributes and look at them, form factors, NAND, and the capacity, some of them that jump out to me are right away are, for example, in the performance side. In client, it's all about IOPS or random access, being ready to go right away. It's not as much about data performance or sustained bandwidth. In the enterprise, it's a mix of both. And in the embedded, it's mostly megabytes per second in the throughput that the applications are concerned about. We've already spoke to the temperature of 0 to 70 and -40 to +85 for embedded applications. The service life, again, is highlighted here. And data retention is another key differentiator between these market segments. In the client consumer side, data retention is really not much of that factor. It's typically considered 1 year, and on the enterprise and data center side, it can be as low as 3 months because the data is refreshed so often. But in the embedded space, the data retention is typically on the order of 3 years, even at the end of life of the drive. On the endurance, we like to measure the endurance in terms of drive writes per day, and in client, it's less than 0.1 drive writes per day. In the embedded industrial space, it's about 1/2 a drive write per day on average. And on enterprise and data center, it's much more. It's 1 to 3 drive writes per day. Reliability is another key factor, and in embedded, especially particularly, you're looking at greater than 2 million hours. MTBF is typically the way that's measured. And lastly, here is the cost. Many people measure them in cost dollars per gigabyte. There are other measurements as well, but in client and consumer, it's the lowest possible cost above all else. In embedded space, it's a low cost, obviously, but it's also is balanced between the cost and the other selection criteria. And in enterprise space, it's low and typically measured, like I say, in transactions per second. So we'll move on into the embedded SSD selection criteria specifically. In embedded SSD, there are 3 fundamental elements. Those are the interface, the controller, and the flash. On the interface side, as we spoke, SATA, USB, SD, and ATA are the predominant ones. The difference between these being parallel versus serial, the performance bandwidth of that particular interface, the number of IOs, and the power. Most of the time in embedded systems, the interface is driven by the host. The host will define what capabilities it has, host controller, and then a systems designer will go and select an SSD based on that. In all aspects, you want a robust protocol for your embedded system. On the controller side, there are 2 key elements: hardware, which is the interface to the host, and also the hardware, the silicon controls the flash channels, as well as ECC and other aspects of how the flash is managed and the data is managed on the drive. The firmware handles the flash translation layer and the efficiencies in which data is written from the host to the drive. Another key aspect is wear leveling and making sure that the NAND flash is worn across evenly. Also, error recovery. As the die lithographies get smaller and smaller, the raw bit error rate of the NAND flash goes up. You need a controller and firmware that can handle those challenges. And as we spoke earlier, is the self-monitoring analysis and reporting technology, or SMART, that helps you track the health of the drive as you go through its life. The controller requires, the key point here is that this is a critical component in the drive, and it requires a proven hardware and firmware solution. Lastly, and most importantly, is the flash. There are different flash technologies. These flash technologies vary based on the endurance, the performance, as well as the cost. SLC, EMLC, MLC, and TLC are the primary NAND flash technologies. And we'll get more detail in the next coming slides. But also the technology node of where the flash is in the life cycle is important, and the performance, endurance, reliability, and cost. So the NAND flash has to be selected based on a balanced solution between these points of performance, endurance, and cost. On the next slide, we'll dig further into the embedded SSD selection criteria: the interface, the controller, and the flash. So as we said, the interfaces range for embedded applications from ATA, or compact flash cards, through USB, SD, SATA, and PCIe. The embedded trend today is a sustaining ATA and USB designs, and on new designs, SATA and SD and eMMC are the predominant interfaces of choice. When it comes to controllers, there are a lot of different companies out there that service and are focused on different markets. I've listed a few here in the slide. For the client side, the controllers are all about cost and not so much about reliability and endurance, because the client is focused on the retail market segment, and again, that drive needs to last 1 to 3 years. And on the enterprise side, there are several controller suppliers that are focused on the enterprise requirements of being extremely high performance, reliability, and endurance, and there's typically a cost associated with that. In the middle are the embedded controller suppliers, and here I have listed 4 of the primary suppliers in the embedded market: Hyperstone, Silicon Motion, Phison, and J Micron. For these four guys, Hyperstone is fully focused on the embedded market, and Silicon Motion, Phison, and J-Micron play in both the client and the embedded space. This is a good thing for all of these guys because with these controller suppliers, they're able to leverage the economies of scale in developing their silicon and go through and touch both the client and the embedded. So most embedded applications are using an SMI, Hyperstone, or Phison controller these days. On the flash side, as we talked about, the NAND flash varies in price as well as reliability. On one end is the TLC, which is largely in the client side, and that has a very low price, raw price per gigabyte, but it also has a very low PE cycle count and more susceptible to read disturbs and data reliability issues. In the middle is MLC. It has a higher PE cycle count and a little bit higher price, but it is very predominantly the NAND flash of choice today. And EMLC, or EMLC, is the same MLC but tailored for the enterprise market, where the PE cycles are driven up to 30K. And then on the very end here is the SLC, which is a single bit per cell. The PE cycles are order of magnitude larger at 100K, and the price that goes along with that is higher. The key suppliers for these NAND flash today are Samsung, Micron, Spansion, and Toshiba. So when you look at all of this information in total, it's very important to go and select the right interface and select a SSD controller supplier that's going to provide you the best solution for your application. And it's really important to look at all of the aspects of that selection. In the embedded trends here on the flash piece, it's largely SLC, but there is a lot of transition going on to MLC. But with MLC, there are challenges in terms of PE cycles, data retention, and the read disturbs, as I mentioned. So the next piece that we're going to talk about are the secondary factors to consider. A supplier versus a solutions provider partner. So when you go, any critical component in an embedded application should include a careful consideration of the supply chain. And here, the critical component being the SSD. What you want to do is you want to identify and qualify an SSD solution provider that is willing and able to sustain the rigorous design-in, qualification, and long-term service support needs for your embedded design. You want someone that's going to be there after the sale. And in that selection process, it not only includes engineering, but purchasing, quality, and production. All those disciplines should be considered in selecting that supplier. From an engineering standpoint, obviously design requirements, data sheets, engineering qual samples, pre and post technical support, even joint qualifications and technical reviews are important. When we look at purchasing, it's more about a stable long-term supply, a partner, a continuity of supply, and a supplier that's focused on the embedded market. And a strategic component, and has strategic component supplier relationships with the suppliers that we talked about on the previous slide. And also about managing the life cycle. When you're talking about a product that's going to be in the field for 8 to 10 years, you want to minimize the number of times that you have to go and requalify a new product, a die revision, a firmware revision, or any change. And you want ample notification of that so that you can plan your resources to make sure that happens in an efficient manner. On the production side, these guys are typically the ones that have the least amount of say in this, but they're concerned with the logistics and the contract manufacturing relationship, if that's applicable. Also, traceability, labeling, and packaging are important. And if there is an issue, they're looking for responsiveness from the solution provider. And lastly, and probably most importantly, is the quality. The standards compliance to ISO and REACH, having a solution provider that provides continuous process improvements, and also has a quick turnaround on failure analysis and corrective action, and making sure that those are monitored for you. So those are the four, at a high level, the four different disciplines that want to make sure that they have some input into the selection process. One of the key aspects, and often overlooked, is the total cost of ownership. The selection should include consideration of the total cost of ownership, and that means not only the initial qualification and the unit price that you're paying, but also any deferred cost in terms of how the product operates over the life and the longevity. And like we said, one of the key things that we have from our customers' feedback is that new qualifications cost them dollars. They cost them resources and expense, and they want to make sure they manage that in a proper way. Another key item here is that if the wrong SSD is selected, then that can lead to problems in terms of requalification and field issues. So you want to make sure that all of these factors are considered and not just the initial price of the unit. From a product lifecycle management standpoint, you want to consider the technology and where you're intersecting that technology for your new design. At Swissbit, we try to make sure that all of our products are on a minimum of a 5 to 10 year life cycle for the product. There will be revisions during that life cycle, but they're managed through a standard PCN process. So when you're looking at new SSDs, you want to ask your supplier where they are in their product life cycle. Have clear understanding of the roadmap of not only their product, but the components that substantiate that product, because you have to keep an eye out for all of that. The continuity of supply falls into really two categories here. With the SLC, there's typically a much longer life cycle in SLC NAND than MLC. MLC typically has die revisions every 18 months to 3 years, but we're seeing a large slowdown in that now. So neither of these are really becoming a big issue. You just want to make sure that that you're able to manage them. Each product change triggers a PCN notification, and each product variation has its own unique part number, and that's one of the values that Swissbit provides to their customers. So with that, what we're going to do is walk into why Swissbit and some of the key takeaways for the discussion today. So embedded applications have a lot of different requirements. There's a product set, quality, technical support, supply chain management, and product lifecycle. On the product set, you want a large, you want leading edge technology, and you may have specific requirements or features that are needed for your embedded application. Swissbit's solution is to provide a broad range of form factors and interfaces tailored for the embedded market. In terms of quality, you want to make sure that there's a quality management and system in place with your supplier, and that you have high reliability. Swissbit's solution is we have ISO standards, we have the automotive standards as well, and we have a thorough qualification process to make sure that our products are ready for the market, and all products in production are tested to the full specification range, 100%. Technical support is a key one in the embedded applications. Technical support is really required worldwide, not only from a design end, but also after the design end and in the sustaining phase of the life cycle. At Swissbit, we offer direct access to our SSD engineers and system engineers, so that it's engineer to engineer and there's no middleman in between that. That gives the most efficient dialogue and exchange of technical information. On the supply chain management, the requirement is that you have worldwide support and logistics. At Swissbit, we have global account teams that manage all of our business worldwide. We have teams in all the continents to make sure that's covered. There's also a stable and reliable supply, and that is key to having strategic relationships with the controller and NAND suppliers. Lastly is a product lifecycle management. You want to have a locked BOM. You want to know that the part that you qualified on day one is the same part that you're getting months later. And to do that, you need to make sure that you have a locked BOM with hardware and firmware. We provide a controlled BOM, we have a change notification process, and to ensure that the parts that you receive are the same that have been qualified. And lastly, here is the longevity. Swissbit offers solutions up to 10 years, and that's as was discussed in the previous slide. Swissbit's flash storage product portfolio includes all the interfaces that we've discussed here: SATA, IDE, ATA, USB, SD, and MMC. The form factors that we offer are a broad range of SSDs, 2.5-inch, 1.8, and M.2. We also offer mSATA and SATA Slim, which are JADIC standards. We have compact flash and CFast. We have micro SD, SD cards, and USB flash drives. The features here: controlled BOM with PCM process, proven power fail protection, lifetime monitoring tools, and tool sets to provide for SDKs and APIs for your own use. Industrial temperature grade is available, long-term availability, local design and support, and product customization. So the key takeaways for today's discussion are that embedded systems cover a broad range of applications and conditions. The usage model, service life, and cost traditionally set the selection criteria priority. Total cost of ownership and lifecycle management are often undervalued in the initial SSD selection cycle. Designers of embedded systems require SSDs and total solution providers that align with their core value set: reliability, endurance, lifecycle, and cost. And lastly, Swissbit focuses solely on the embedded OEM industrial market and offers an extensive line of SSDs and services and support for the most demanding applications. For more information, please contact our Swissbit website as shown. And I'm going to hand it back over to Nick now for open discussions.
All right, thank you, Grady. All right, we will take a look and see if there are any questions out on the Twitter feed or through our Google Plus account. All right, we do have one here. So the first question, Grady, for embedded applications, what are the most popular form factor solutions and why?
Thank you, Nick. For embedded applications, the most popular form factors are typically the smaller ones. A 2.5-inch drive is typically not an embedded application. But SD cards, compact flash, CFast, and so when it comes to SATA, M.2 is one of the key new designs. So most embedded applications that are going through new design are either using M.2 or mSATA form factor to meet their requirements. And if it's not, and especially if it's needed for performance, if it's more about storage and performance is not a key factor, then SD cards or micro SD cards and eMMC are the typical factors of choice.
All right, excellent. Let's take a look and see if there are any more questions. All right, we have another one here. What can system designers do on the host side to extend the life of their SSD in their application?
Thank you, Nick. On the host side, it's important to understand how you're using the drive, and the usage model can help. You can tailor that usage model to help extend the life of the drive. In terms of, there's typically people are have torn between should I use SLC or MLC. If they have a good idea of how their host is using the drive, they may be able to save cost by using MLC-based drives. One of those criteria are the way the host writes to the drive. Typically, large volume of random transactions drive a lot of writes on the host. A lot of writes on the host means that the NAND flash gets worn more quicker. So if the host system designer can go and change the way that they write to the drive, they can go and extend the life of the drive by managing that drive write per day parameter that we talked about in the presentation. Another key thing is to talk to your solutions provider and have a technical dialogue with the system design engineers and understand exactly how the drive is being used. And we can make suggestions for you of where that can be improved. Another key thing is using the health monitoring. The drives today have come a long way from the drives that we had in early 2000. Today the drives can tell you, hey, the gas tank is about empty. You need to go and exchange this drive. Or it can give you other parameters about the health of the drive. So again, Swissbit has a lot of information on our website and white papers that we can share with our customers that really go into the details of those. The trim command is another one that's used quite often to help keep the drive clean and healthy. Thanks.
Excellent. So you just mentioned the health of the drive and the longevity. I know Swissbit is known for the smart report technology. Would you be able to touch on that? How you can use that to monitor, predict the health of your drives?
Sure. So smart reporting technology goes back into the days of hard disk drives. It's been around forever, and it is part of the ATA spec and standard. The key thing that's a differentiator between Swissbit and other companies is how much information is put into that. Smart reporting is, like I say, an ATA command. You issue that command, you're going to get back something. But the specification, the industry spec, doesn't say what the quantity or the quality of the data is that's provided back to the host. At Swissbit, we put a lot of effort into making sure that our products provide valuable data that's been verified and is really over the top in terms of providing additional feedback to our customers on how the product is doing. So we put a lot of effort in making sure that it's very verbose, if you will, in terms of the different parameters that are report back. For example, how the life cycle is measured. Life cycle can be measured in a couple of different ways. It can be measured as strictly just how many array cycles you've done on the drive over the life of the product, which is kind of a linear measure of the health of the drive. For every drive write, that clicks off a program array cycle for all the NAND. And as I approach, for example, MLC, up to 3,000 program array cycles, and I'm approaching the end of life of the drive. There's another way, and that is to measure the number of remaining spare blocks in all drives, whether they're an SD card or a SATA drive. There are spare blocks that are allocated that the user can't see that we use to replace marginal blocks or blocks that have gone bad. And that spare block count, or the bad block count, typically increases as you go towards the end of life of the drive. So it's not as much of a linear indicator, but you can use both of those, and we have as good tools to help understand where the life of the drive is. And we have white papers on these types of techniques of how to make sure that you get the most out of the drive. So it's really, again, SSDs have come a long way. They've had to because the NAND flash continues to shrink, and the die lithography is down to, it used to be back in the day we were at 120 nanometer. Now we're talking 15 nanometer. And with that type of process shrink, something has to give. What gives? The raw bit error rate of the NAND and the susceptibility to read disturbs and these types of things. So you want to use all the tools at your disposal to make sure that the drive sustains a reliable endurance throughout the life of the product.
Thank you, Grady. That actually leads into the next question quite well. You mentioned ever-increasing die shrinks and technology shrink and NAND flash. The next question is, what do you think the limit is, and when do you think the next technology will replace that?
So there's a lot of information out on the market about this topic, and a lot of discussions and good feedback from the industry experts. The planar NAND flash cell is currently for SLC, it's at 24 nanometer, and for MLC, it's at 16 nanometer, 15 nanometer. And there's really this, don't believe that there's much more to go beyond that. You just can't get any smaller. So most of the information that I read and and understand are that the planar NAND will be around through 2020, And in the meantime, these guys like Samsung, Toshiba, and the other guys are developing 3D NAND and some other types of NAND technologies. All of those, it's one thing to say, yes, we have it and we can see it working. It's another for it to really be in the marketplace. And then the other key element is once it's there, does it fit in the embedded applications, or does it just fit for client, consumer type of applications? So we'll have to figure all that out as we go over the next few years. It should be very interesting, but we see very solid and sustained support for SLC and MLC throughout the rest of this decade, and we'll be closely monitoring the developments in the industry for NAND flash going forward.
Oh, excellent answer. Thanks once again, Grady. We'll open it up and we can maybe take one more question. So, okay, we do have one last question here. So in terms of understanding the usage model of an embedded system, what strategies can be used to measure the workload of an embedded system?
Thank you, Nick. So the way that we can do that is, like I said earlier, for embedded systems, Swissbit likes to work directly with our customers and ensure that we have a full understanding of their use model. And with the health monitoring tools and the reporting that comes back from that, we can measure certain things such as the number of unexpected power cycles. More importantly, we can measure the write amplification of the drive. The write amplification is driven by the number of writes that the host does to the drive, and how efficient is the controller at managing those host writes into the NAND flash. This is a key part of the flash translation layer in the controller. Typically, controllers have two different types of architectures that they approach this. One that's been around forever is the block mode architecture. Block mode is that everything is managed on an erase block in the NAND flash. A more efficient and more recent development is a page mode architecture. Page mode manages all the NAND in terms of pages, which are subsets of a block. The key benefit for page mode architecture is that the write amplification is greatly reduced over different workloads. If you're doing a sustained writes where you're doing just a lot of large file transfers, then typically it's all sequential data. Typically the write amplification will be on the order of 1 to 2, meaning for every chunk of data I write from the host to the flash, it costs me 1 to 2 chunks in the flash. And on the other end of that spectrum is random writes, where if you write a large number of random writes, how much does that cost to write it to the NAND flash? All of this is very important when you're using drives that have MLC NAND and have a limited number of program erase cycles. So the latest developments are with these two, and what we do is we can measure these through the health data and track exactly how many writes the host did and what that did to the drive over the course of a 24-hour or a week period, and say, okay, this is, we can measure the actual write amplification, and then be able to help our customers understand how long is this drive going to last reliably in the field. There are some standards out there. JADIC has a very nice standard for measuring workloads. The unfortunate part of it is that standard only addresses two key markets, bookends, being the client side and the enterprise side. Because embedded has such a wide variance of usage models, JADIC doesn't specify a usage model for embedded. So a lot of customers say, well, all right, I don't have one. What am I going to do? I'm going to use the enterprise, or I'm going to use the client. And what you may be doing is actually, and while those are a measure, what you may be doing is being too conservative or shorting yourself on the actual usage that your embedded system has on that drive. Again, we want to help our customers get to the lowest cost solution, but we also want to make sure that we provide a solution that meets the expectations of that product field, because at the end of the day, it's our customer's brand that is on that product. and we want to make sure that there aren't any problems there. So our strategy is that we like to work directly with our customers, understand their requirements, give them some ideas on how to do how to measure their own workload better, and help them make the right selection for their SSD requirement. Thank you, Nick.
Yeah, thank you, Grady. Excellent answer. Excellent presentation today. We do have more information on Swissbit SSD migration and a number of other topics. Visit Swissbit supplier page posted on Digi's website. So go out and check out the supplier. We have some other training modules out there for more information. Today's presentation will be available on YouTube channel going forward from here. And I'd like to thank all the viewers for joining us today. With that, thank you once again, Grady, for stopping into Thief River and taking that on your schedule. And I believe that is a wrap for today. So if there are any more questions about the field, go ahead and get on our Twitter account, hashtag KHOA, or get a hold of me through any of the main channels, or else you can also contact Swissbit through us as well. So once again, thanks everyone, and have a good rest of your day.